Hello everyone, good afternoon for those who are in Indonesia, and also good morning for Nikolaos and Prof. Patras. Um, my name is Dian. Today I will be moderating for today's webinar. Welcome to the workshop on moment tensor inversion using ISOLA. We are honored to have a distinguished speaker, the developer of ISOLA and Gisola with us today, Prof. Sokos from the Institut of Patras, Greece, and Nikolaos from the National Technological University of Athens, Greece. Additionally, we will have an opening talk by Prof. Andri D, Nugraha and Dr. Sahara from Bandung Institute of Technology, Indonesia. Before moving on, please allow me to inform the event agenda. Okay, this is the event agenda. So we will have 3 sessions. The first session will be an opening talk from ICB, followed by the session, and the third session of presentation about ISOLA from Prof. Sokos, and followed by presentation by Nikolaos about ISOLA. And the session will be end with a discussion on possible collaboration. Okay, without further ado, let's start our first session. I would like to invite Prof. Andri D, Nugraha, the head of the Global Geophysics Research Group at ITB, for the introduction. Prof. Andri, the floor is yours.
Okay, thank you, Dian. Good day, good morning, everyone. Assalamualaikum warahmatullahi wabarakatuh. Selamat siang semuanya. Allow me to introduce myself. My name is Andri D. Nugraha. I am a seismologist from Global Geophysics Research Group, Faculty of Mining and Petroleum Engineering, Institut Teknologi Bandung. The honorable Mr. David, Head of Geophysical Engineering Study Program ITB, Professor Efthimios Sokos from University of Patras, Greece, Nikolaos Triantafyllis, PhD, National Technology Unit of Athens, Greece, and also our college and distinguished guests who attend today in online workshop. The topic is moment tensor inversion using Gisola, hosted by ITB, UPSL, and Patras. Yeah. Actually, as we know, Indonesia is located in active tectonic and complex geological setting due to the relative major plate motion, including Indo-Australian plate, Eurasian plate, Pacific plate, and Philippine plate. So actually, this situation produce high seismicity activities, and also there are active volcanoes in the area. In seismology, understanding earthquake source process actually phase identification, hypocenter determination, magnitude calculation, and also local mechanism analysis are very important tasking for earthquake early warning and also for seismic hazard mitigation. So I think the topic of workshop today is very interesting and very important for us to learn more about the source mechanism of the earthquake. Actually, the closing, I enjoyed this workshop, and hopefully it will be useful, in particular for the researcher and student. Actually, here, actually from many institutions and also many universities, there are bachelor student, master student, and also doctoral student. Again, thank you very much for the keynote speakers today for the sharing knowledge. Thank you, Dian.
Thank you, Prof. Andri, for introduction. Next, we will have a presentation by Dr. David Sahara, as the head of the Geophysical Engineering and the Geology Department at ITB. Dr. David, the floor is yours.
Okay. Again, can you hear me?
Yes, please.
Yes.
Okay, so okay. Can you see my screen? Okay, so Good afternoon, everybody, and also good morning, Professor Sokos and Nikos. So I would like to give an overview of the seismicity study, or SCUBE, or we call it seismicity stress structure study in the Global Geophysical Research Group. So I see here, I hope that after this workshop, there will be collaboration in the future between maybe among the participant, or between the ISOLA with us or ISOLA with other participants. So we would like to give an overview of what we do especially in the Global Geophysical Research Group related to the seismicity and structure study. Okay, so this is the Global Geophysics Research Group. We are a research group in ITB, and there are 14 members, in which the head of the research group is Professor Andri, the one who gave introduction to this meeting. And we have also honorary members or honorary professors, Professor Rob van der Hills from MIT, Professor Phil Cummins, Nick Rawlinson, and also Professor James Russell. So we have a relatively huge team here, supported by student, master, doctoral, and also bachelor. So we perform some joint research between us. And if we see from the publication, we are quite active in the last couple years, that we actively publish our joint research, and the citation is you can see here, just for introduction. And there are several papers that have been published recently in 2021, 2022, 2023, mostly in terms of the tectonic and also seismic imaging. For instance, Professor Andri, he is a professor in seismic tomography. I would like to go a little bit into Indonesia, in which maybe we could set up a collaboration in the future. That in terms of the tectonic setting, it is very interesting, because there are a lot of plate interaction in Indonesia, in which makes the seismicity activity is quite high in Indonesia. And BMKG up to now, they have already installed more than 500 seismometers. And some of our students, or maybe some of the BMKG staff, are studying at ITB, and they conducted some research related to the data from BMKG. And also some of our students are also asking permission from BMKG, and also working in the larger regional scale by using the data from BMKG. In addition to the data from regional network, we sometimes also deployed our local network, especially after the major event. We have several places, for instance, the one in Aceh 2016, and also in Ambon 2019, in Lombok also 2018, and also the recent one is in the Cianjur, which is in 2023, if I remember correctly. So okay, so there are several data that students are using for their study. And we would like to introduce that we are also in the very early phase, I would say, in the fairly early phase to develop our real-time seismic processing, because we got support from BMKG by using the iDrip scheme, and we develop our seismic processing. So it's a real time, and then it's a web-based, so it's easier to use, and also easier to manage. And we put artificial intelligence base for algorithm for the seismic processing. Once again, this is in the very early stage. We just start this year, so we are still at the beginning. And so of course we hope that if this seismic processing software could be achieved, then we can implement a lot of algorithm to the incoming data. For instance, if we have succeeded in managing the incoming data, the real-time incoming data, and then by using our architecture, it's possible to put some module and then add to the system. Okay, so next one, I would like to give a highlight on Dian. So she is the one who organized this workshop. So it's this workshop can be possible to it is possible because of Dian. So Dian make contact with Nikolaos and also with Professor Sokos, and to organize this workshop. I think the participant who want to join this who register is around 83. So it's I think we should give a big applause for Mbak Dian. So she is our PhD student now, is finalizing her study, and she made a lot of research with ISOLA, in which two of them are published in PEPI and also in the Journal of Earthquake Engineering, in which she want to analyze more in the Palu Koro and Matano fault, which is in the eastern part of Indonesia in the Sulawesi Island. And before this study, the available seismic focal mechanism data from international catalog maybe around 10, if I remember correctly. So 10 to less than 15. And in this case, we have the data from BMKG. There is an agreement, and in terms of, I think, around 5 years, we got more than 100 events. So by using this new catalog data, Mbak Dian investigate the seismicity analysis around the Palu Koro. So I would like to skip this one. So as we know that there is a seismic active area in the eastern part in the Sulawesi Island, for instance, especially, and the aim is to analyze the fault strength in terms of the friction coefficient along the segment in Palu Koro and also the Matano fault. And then we want to compare and analyze the seismicity pattern and also the frictional strength. And in addition, we would also put the numerical modeling on top of our results. That's what Mbak Dian did for her PhD. In terms of the data, we use the International Seismic Catalog, as I mentioned before, and we also using the data from BMKG in order to produce the new catalog of focal mechanism. Okay, I would skip this part, and this is the result, in which, so now we have a more detailed analysis about the focal mechanism and also seismicity around along the Palu Koro fault, in which we know the friction strength along in each segment of the Palu Koro and also Matano fault. And by analyzing the discrepancy between each segment, and then we somehow correlate with the seismicity pattern in that area. The result number 2, by using this one, the result number 2 is that we produce 100 new catalog from the focal mechanism. And here, afterward, we make a more detailed analysis of the mechanism in each segment. Because before we know that it is a strike slip, but now we know more detail that it is in some part it is oblique and it's mostly dominated by other mechanism, and then we try to understand it now by implementing numerical modeling afterward. So I think it's very interesting. It is very important to have more data, especially for the focal mechanism data in Indonesia, to have a better understanding about the fault pattern, the frictional strength, also maybe in the in situ stress in that area. If we can somehow mimic this procedure to other area, it will be a great opportunity in the future. Okay, other results also not from Dian, but VD. He is maybe junior of Dian, and now is continuing his PhD in Korea. And then he made an analysis of the focal mechanism as well in the Ambon earthquake, the aftershock. So there is a big, there is a 6.5 earthquake, and then this 6.5 triggered another segment, which is and create even with magnitude of 5.2, and in which VD in his master thesis, he made kind of seismotectonic analysis how one major fault reactivate a small one, and then from reactivating the small one, it leads to a major fault with also create a big event in the Ambon area. So I hope that it can give overview of what we are doing related to the moment tensor inversion. In addition to the tectonic, we also do kind of the more local area. Is a publication from Mas Joko in geothermal area. So we made also collaboration with some geothermal company. The newest one with the Geodipa, and then in which we deploy more than 10 stations. And in this case, we also using the data and invert the focal mechanism. And by using the focal mechanism, we make the conceptual model of the reservoir in the geothermal field. Okay, this is our publication from Mas Joko. And another example of how we do also, how we implement also the focal mechanism, we have also collaboration with the mining company. The publication can be found here, in which we try to monitor the development of a cave by using the seismicity pattern. And from the seismicity pattern, we could also infer the focal mechanism, and we know how the mechanism of the growing of the cave in the underground. So there are several aspects that we cover in terms of the focal mechanism. Hopefully, this workshop will accelerate us to do more analysis in the other area. I think that's all my presentation. Hopefully that you can grab some information of what we do, enjoy in the workshop, and we are very open for collaboration. And once again, thanks for Mbak Dian, at least 83 participants from university and also from the company join us in this afternoon. Thank you.
Okay, thank you, Pak David, for your presentation. We will now open for discussion or a small Q&A. If you have any question or response to this question, or you can refer them directly. Maybe Nikos or Prof, you want to give response or ask questions? Yes, Prof, you may verify your question.
Good morning, everybody.
Good morning, Prof.
Sorry, Diana, I cannot hear you very well.
Okay.
I don't know if it's a problem with the microphone. I would like to thank you for the invitation. I was very surprised to see the number of the participants. We are not used in this number of participants in the seminars we participate. And I see that there is a lot of interesting results from your group. You are very, very active and very, very nice results indeed. I am okay. I will discuss more later about what we are doing here in our lab. But we are very much interested in seismotectonics because we are also in a very active area, and we are doing also similar studies. I would like to have a list of some of your papers so I can have a better look and have a better idea of the results you are getting. But they are very, very interesting. Thank you for the presentation, David.
Sure, thank you. I will send you the list. Because I mean, it's a very brief presentation, and we should definitely need to discuss it later.
Okay, do you have any more questions or response?
Yeah. Next session.
Ya, Pak David. Okay, do you have any more questions or response? Maybe if not, this time we will move on to the next agenda. We have a photo session first. I would like to ask the participant to open the camera to have photo session.
I think Diana asked if Professor Sokos has a presentation to share.
Yes.
So you suggest maybe, or we do little bit of this photo first, or maybe just short one, and then after that we can move to the next one.
Sorry, but I cannot hear Diane very well. Nikos.
Yes.
So my presentation is later, right?
Yes, your presentation will after this session.
Okay.
We just want to have Diane ask us to open the camera, so we will have a kind of a photo session.
Okay.
After this, maybe we can move to the next one, and if I remember correctly, so the next one will be your session.
Please open the camera and participants. You still waiting. Because if you join us to photo session, then you open the camera. Thank you. Please, Anita, or would you please help us the photo session? Asmi, thank you help for the photo session. Could you give code for the photo session so the participants can prepare their best smile in the photo, please? Asmi, do you hear me? Or maybe Ila, could you help me for the photo session and give a code like 1, 2, 3 so we can prepare our best smile? Yeah. Risha, could you help me for the photo session, please?
Of course, by the end. Okay, I will get the photo session because there are 2 screens in my screen, so there will be 2 ticks for each screen. For the first screen, please prepare your best smile as said by Madian. 1, 2, 3, smile. Hold, please hold. The second photo for the first screen. 1, 2, 3. Okay, hold the smile. Okay, thank you for the first screen, and please stay on camera. For the second screen, we will take 2 photos. Okay, smile in 1, 2, 3. Okay, one more photo. Please keep your smile. We'll take photo in 1, 2, 3. Okay, thank you everyone, and thank you Mbak Dian.
Okay, thank you, Petia. Thank you, everyone. We will move on for the next session. Perhaps because we start in so we save some time, so we can move to the next session now. Prof. Sokos, the time is yours. You could present the speaker, please. Thank you.
So, hello, everybody. I am Professor Efthimios Sokos. I'm from Greece. I am a professor of seismology and engineering seismology in the University of Patras. I have a very small presentation of our lab. I will try to share. Is it okay? Can you see my screen?
Yes.
Yes, clear.
Okay, okay. So very small presentation about our lab. Just to say a few things. The university Patras is located in Western Greece, and 1 minute. Okay, here. Okay, you probably do not know about the seismotectonic context in the area. So I have a small map here. So we have a subduction here. This is the Hellenic subduction. We have a big strike slip fault here. Then we have collision here to the north. And this is the North Anatolia fault that comes from the Turkey towards Greece. Then we have extension in the Aegean area. This is the Aegean with all the islands. Sorry. Okay. This is the green star is where Patras is located, and the red rectangle is more or less the area of our network where we have deployed our stations. This is a seismicity of Europe, and as you can see, the seismicity in Greece is very, very intense. We have a lot of probably most of the seismicity in Europe, and this is a better view. You can see the earthquakes here from the subduction mainly. This is the North Anatolia here, coming into the Aegean. The strike slip fault I spoke before. This is the big fault here. It is called Kefalonia Lefkada strike slip fault. Patras is located here. It's very close to a very active rift. This is the Korinthiakos rift. It's a continental drift with a lot of activity. And this is the first network we installed in the 90s. It was based on analog transmission. Now everything has changed, of course. This is some historical records. This is the new permanent network with the digital transmission, etc. We are part of the Hellenic Unified Seismic Network, which is the national network of Greece that is a combination of the University of Athens network, the National Observatory of Athens network, the Thessaloniki University Seismic Network, the Patras, and the Crete Seismic Network, and plus the stroke motion networks of the two organizations in Greece that record they maintain stroke motion networks. Now, most of our stations are have collocated broadband stroke motion instruments. Some of them, and they also have GNSS instruments. And all the data are shared through the ADA node that is hosted by the National Observatory. So we are not actually involved directly in routine, let's say, processing of the seismicity. The responsible within the national network is the Athens National Observatory for this, but we provide all our data and we cooperate closely when we have some strong event to deploy temporal arrays and so on. Just a view of the seismicity in the area. It's very intense. Of course, you know the software we have developed together with the Technical University in Czech Republic for calculating the moment tensors. We routinely use it to calculate the moment tensors. Here you see some of our database, some data from the moment tensors. And also temporary seismic networks for various reasons, for monitoring aftershocks, for doing tomography, and so on. We have a large pool of portable instruments and some maps of recent strong earthquakes in the area and some analysis. I will speak about some of them later, so it's not so important for now. So I stopped here with the presentation for our lab and in general the seismicity. If you have any questions for this, if not, I can continue with the ISOLA presentation. I guess there is no question, so I can move to the ISOLA. Diane, your mic, yeah.
Okay, could you hear my sound now clearly?
Yes, now, yes.
Okay, sorry for the problem. Maybe we could move on to the ISOLA. So if we have Q&A all together for the presentation and the ISOLA.
Okay, so I move to the next presentation.
Thank you, Prof.
Do you see the screen? It's okay?
Yes.
Okay, good. So I have tried to make a presentation. I don't know how advanced you are. Obviously, some of you are very advanced with ISOLA use and the moment tensor processing. So I tried to have some small theory and some applications and also a small overview of the software. Of course, you know, the time is very limited, so we cannot discuss many things, but we can use the time for Q&A, or you can contact me via email or later. So the overview of the presentation is like this. I will start with a small history of the ISOLA. Yesterday, I realized that it's 20 years of development for ISOLA. I was preparing the presentation and I realized that we started in 2004, roughly. Then some small, few slides about the theory of ISOLA and a short overview of the graphical user interface and the various options you can have. And then I will finalize with applications. Two types of applications. ISOLA can compute either point source for a seismic event, or this is, I would say, the power of the software that can use it to derive multiple point sources from a big rupture. So, small history, as I said, the development of ISOLA, it started in summer 2003. The core of the software is in Fortran that does all the calculation, the inversion, and so on. And there is also a GUI, as you probably know, which helps the user. It makes it easier to interact with the software, to have plots, to have almost publication-ready graphics, and so on. The first version was released in 2004. It was after my I had a very long, I had a sabbatical in the Technical University, and we developed the software and did the first release with Professor Zahradnik. We are now close to make a new release of the software that it will have some let's say big changes, but the basic things still remain. It will be faster, I would say, and it will have more tools to derive the uncertainty of the solution and so on. It has been used, the software has been used in a lot of papers. It is a routine analysis software in various labs. And of course, some other versions emerged from ISOLA. The SC ISOLA is abandoned by Nikos now, and G ISOLA is more known, but there is also Bayesian ISOLA by a student of Giri Zahradnik. So many versions of the software. So from where the name ISOLA appears, it's from the word isolated asperities. And what do we mean by the isolated asperities is that when you have a rupture, let me find the cursor here. Okay. Okay. So when you have a rupture, you start from the hypocenter, then after some time you have an asperity, the break of the asperity, and finally this propagates and you have such a view of multiple asperities. ISOLA comes from a method by Kikuchi and Kanamori, which they develop an iterative deconvolution of multiple point sources. What does it mean, iterative? That we define in an iterative scheme the main asperities of the rupture. So we can call the asperities, sub-events, okay? So we retrieve one by one the sub-events from this multiple rupture. So this is the isolated asperities. This is the name of ISOLA. So the moment tensors of the sub-events are retrieved by least squares minimization. And besides the moment tensor, we also find the optimum sub-event position and timing. So we find the timing. Somebody could call it, it's like a sleep inversion, but it's not a sleep inversion really. So to find the optimum sub-event position and time, we find it by grid search over time and space. Space can be either a point, multiple sources or sub-events under the epicenter, or it can be a fault plane that we discretize and we find all the point sources, all the sub-events on the plane. It can be applied in regional and local distances. The green functions are computed by the discrete wave number method of Buson. And as I said, it has a very good graphical interface, and it interacts with GMT, Google Earth, and outputs the results in ASCII files and so on. So a few words about the theory of ISOLA. It's a very simple theory. If we consider a point source, we can have this equation here. The ground displacement is it's this one. And it can be described as a convolution of the moment tensor and the green function. Now we assume that green functions are known. We know sort position, we know crustal model, and in this way we can compute the green functions. I have to say here that we assume that we know the green functions. It means that there is some sort of error coming from our inaccurate knowledge of the crust in this part here. Then we are not, in ISOLA, we are not using directly the moment tensor, but we do a small trick. We describe the moment tensor as a linear combination of 6 elementary tensors. You see the 6 elementary tensors used in ISOLA, and here to the right is the elementary tensors used by the Kikuchi and Kanamori method. They are slightly different, but this is a technical matter. What we are actually looking in the inversion is these coefficients here. So these coefficients describe the relative proportion of these 6 let's say, elementary tensors in the final solution. Now, if we combine the two equations, we will finally end up with this one, where this Eij here denotes the elementary seismogram. Elementary seismogram means that this is the MT combined, the moment tensor combined with the time function. And as a time function, we use delta, which is a good approximation if we are working below the corner frequency of the event. So this is the basic equation here. We have connected the displacement with some coefficient and some elementary seismograms. And now this equation can be written in a matrix notation here. And this equation now in a matrix notation can be inverted using least squares in this way. So in this way, we find the A's, and this is done by minimizing the difference between real and synthetic data using L2 norm. The A's can be later used to define the final moment tensor, the moment. Okay, from the moment we can get the moment magnitude. And we have also some other indices here. We have the correlation. This is the real data. This is the synthetic data. We have the misfit, which is defined in this way, the variance reduction. And the correlation is connected with the variance reduction using this equation. The correlation is the square root of the variance reduction. Okay, I hope it was not very, it was clear. First, I tried to not say a lot of this theory. As I said before, ISOLA is trying to find the optimum position in time and space of the moment tensor. Either a single moment tensor if we want to model the source with one moment tensor, or with multiple sub-events. So it will find the best timing and the best position of the sub-events on a fault, for example. So this is a very basic, let's say, very useful diagram. We see here our time-space grid search. We are looking at the 0 is the origin time, so we are searching for the centroid time -3 seconds before the origin time and +3 seconds after the origin time. And on the y-axis, we have the source position. Now, the source position, I said, it can be just under the epicenter. It can be on a line with some inclination. It can be many things. It can be also a fault. So in this correlation diagram, we see that this is our best solution. So the retrieved moment tensor is found a few, maybe half a second after the origin time. This is the area of the best correlation. And as you can see here, we have a very stable focal mechanism. The coloring of the focal mechanism is based on the double couple solution, the double couple percentage of the solution. So now, using this correlation diagram, we define two quality metrics in ISOLA. And the first quality metric is trying to derive the stability of the focal mechanism. The idea behind this is that, okay, we have the best, let's say, moment tensor, the optimum solution, but how stable it is? How much does it change in space and, in space and time? So to derive this, we set a threshold. We say this is a bit arbitrary, but okay, we define a value 90% of the maximum correlation. So this is the maximum correlation. And based on this 90% of the maximum correlation, we define an area on the correlation diagram, and we select all the solutions. We get all the solutions that are above this threshold. Now, within this small area, we take all the solutions and we calculate the Kagan angle between all these solutions and the best solution or the reference solution. For those that you are not familiar with the Kagan-Nagel, the Kagan-Nagel is a measure of the difference of two double couple mechanisms. So small Kagan-Nagel means that our focal mechanisms are the same. And to get an idea of what does it mean small, values below 20 or 30 degrees of Kagan-Nagel, they are considered as similar or similar focal mechanisms. So once we do this, we then calculate the distribution of these Kagan-Nagels, and we calculate the mean value and some standard deviation. This quality metric is called in ISOLA FM-VAR, focal mechanism variation. And as I said, it tries to capture the variability of the focal mechanism in the neighborhood of the best solution. So this is the first quality metric based on the correlation diagram, because there are also others. Another quality metric is the space-time variation. Okay, we found our best solution, but how big is the area that could perhaps contain the best solution? To do this, we again set a threshold. We found the area S here, and we calculate the ratio S divided by the whole area we used in our inversion. And this is a measure of the stability of the source position and time. If it is small, it means we have defined very well the timing and the position of our centroid. And you can see here some examples. This is a very good solution. We have Kagan-Nagels very small, FM-VAR is 17, ST-VAR is also small. This is an interesting situation here. You can see that we have a good correlation area here, but we have this small area here with also similar correlation values. I don't know if you can see from the resolution, but the focal mechanisms here, they are exactly the opposite from this one. So you get a very high Kagan-Nagel here. But this area here is at 3 seconds after the origin time. So in principle, we can consider this is an artifact, and we can stop the time search earlier, so we can remove this one. This example here, it shows good stability in the focal mechanism, although the area here is very, very large, and the space-time variation index is very large. So we have found a good focal mechanism, but we are not good in the position and the timing of the focal mechanism. So this is roughly the theory and the quality metrics of the ISOLA. Of course, the basic quality metric is the variance reduction. How good is the fit between the synthetic and the observed data? Now, I will go fast through the main GUI windows, and then I will continue with the application. So this is the first the first GUI, where is when you start ISOLA, this is the first form you see. And the idea is that you start from the left and you propagate to the right. So you start by some utilities. You have to define your poles and zeros from your stations. You start by importing your data. ISOLA needs the data in some ASCII format. So there are tools to convert from Miniseed, from SAC and other formats to ISOLA version, to ISOLA format. And there are tools to inspect the data for the noise, rotate data if they need rotation, and so on. And then you start with the event information. You define your crustal model. There is an option of defining multiple crustal models. If you do research in an area where you know that your crustal model, your crust is 3D and you have various models, then you can use up to 4 different models for your stations. Then you select the stations you are going to use. prepare your data. Data preparation means that you correct for instrument response, you resample, you time align your data and so on. Then you define the source position, the grid of the trial sources, you compute your green functions, and then you go to the waveform inversion. And finally, plot results and so on. There are also some other tools. I will not speak about them now. I will start with the crustal model. It's a simple tool. ISOLA is using 1D model. You just put here your VP, VS values, your density, and your quality factors. And the last layer has to be the MOHO. As I said, you can also have multiple crustal models, but this option is not used very much by the people. I don't know why, if it's complicated or there is no much information about multiple models. Now, the next one is to give some information about your event. So you have to put the coordinates of your location. You have to input the origin time. And also important is to define the time window length, which is the portion of your waveforms, the duration of the waveform that will be used for the inversion, starting from the 0, which is the origin time. Lots of people ask why we have these strange values here. These strange values here come from this equation here, because we have a fixed value of 8,192 points. I have to say here that for the new version, this is not true. We have reduced this value in the new version. So in order to get, let's say, a better DT value, you have to define some strange TL value here. TL starts at the origin time, which means that based on your extent of your network, on your stations, you have to define some value here that will incorporate all the time window within of your signal in this values here, in this time window length. Select stations is simple. You give a file with your station coordinates, and you get the map, and then you can select the station you are going to use using the mouse. What is important here is that if for some reason you want to change the epicenter, you found a better solution and so on, then you have to repeat this step, okay? Because all the green functions are calculated using the epicenter location as the 0. This is the tool for defining trial sources. The most common option is to define sources below the epicenter, with starting from the depth, with step and the number of sources. But you can also define sources on a line or a plane, which is more complicated and used mainly for large events. Okay, you get also plots and so on, such stuff. Now the data correction GUI, you import your data here, and your data are corrected for the instrument correction time. They are aligned for time, resampled. There is a tapering at the edges of the signal, and you can use either velocity or acceleration. But ISOLA always assumes that your signal is in velocity, which means that you have to take care in the pulsed zeros if you are going to use acceleration. Now, this is a very tricky step. We get a lot of comments by people why we are not using some automatic tools. Now Nikos will talk later about the automatic versions of all this stuff, but we do not prefer, let's say, so much all this automatic procedure, because there are problems in the data. You see here an example. You have a small event. The epicenter distance is 12 kilometers, and of course, you will have long period noise. So when you see this type of noise, you have to take care of it, and this is why we have this pre-filter here in this tool. If you do not use it, then you will send this signal for the inversion, which is noise. But if you see this during the procedure, then you can pre-filter, and then you get a very good signal that can be used for the inversion. So all these things, this is just an example. There are many other disturbances that can be in the data. This is just an example to tell you that you have to be very careful with the data. The data have noise. They might have noise in higher frequencies. They might have noise in lower frequencies. They might have some disturbances. So we prefer this manual, time-consuming procedure, but we have all the time eye contact with the data, so we can find that something is wrong. Finally, the inversion. You can define the inversion type, your frequency band, you can remove components, stations, you can apply weights, you can have different frequency bands per station. And from this tool, you can also use other inversion methodologies we have included in ISOLA, using, for example, the CSPS method, the envelope method, or spectra method, and so on. And from this, you can also plot the correlation plot to get an idea of how good is your inversion. And finally, the data plotting, where you can plot maps, you can plot observed versus synthetic data, you can compute FM-var, ST-var, and so on. You can also do forward simulation in ISOLA. So if you have a moment tensor, if you have a solution, you can do forward simulation to your stations to see how well your stations fit in some solution. And finally, you can do jackknifing. This is automatic now. You can remove stations, components, and then you can have a plot, a sum of your results, and you can see how stable your solution is. This is a very good example of the jackknifing. And finally, I can move to application. I don't know about timing. I probably took a lot of time, right?
You can still proceed for the presentation. We still have time.
Okay.
Thank you.
Sorry for my voice, but I had the COVID and now I am in the process of recovery. So applications. I will just show you some plots of papers produced by either our group or from other groups using ISOLA. And I will start by earthquakes model as a single point source, which means that we have to do with either small events that we monitor from very local, let's say, distances, and or we are using long wavelengths, longer than the fault, so lower frequencies, and large epicentral distances, longer than the fault. Here we have to be careful because the epicentral distances, they should be short enough in order not to have problems from the inaccuracies of the crustal model. So I start by an example for using ISOLA to analyze microearthquakes. You see the magnitude here is 0.8 to 1.4 in central Brazil. These are data from local networks. You can see here the scale is 4 kilometers. So we have very small events, very small distances, and you can use frequencies as high as up to 1.5 hertz. This is possible because you have very small distances, station event distances. And then you can use the ISOLA uncertainty tool and get some idea about the uncertainty of your solution. This is from Carvalho et al. Paper. This is another, let's say, methodology. This is a methodology. When you have few records, you don't have many waveforms because, for example, the earthquake is not so large, the station is not so, the network is not so dense. so you have good quality records in a few stations. But still you have enough, let's say, polarities to compute a rough focal mechanism. So what you can do, you can get such a solution using the polarities, which is a mixture of many, let's say, possible double couple mechanisms. And then you can get all these solutions. You can give these solutions to ISOLA with a few good records. And then ISOLA will go through all these pairs here. This is called the cyclic scanning of polarity solution. And will find all the solutions. Hopefully that will be a small portion of all this that will fit very well the few waveforms, but still they will be also compatible with the polarity. So it is a hybrid method using polarity solution and waveforms. Waveforms at few stations and polarities from more stations. This is some extreme, let's say, application of ISOLA using a very deep, 600 kilometers deep earthquake, but a very large event in South America. And we analyzed this event. It was actually a doublet with ISOLA. This is also very interesting. This is the papers from the nuclear explosion in North Korea in 2017. What was interesting in this example here is that there were two events, let's say, recorded. It was the first event was the explosion, but the second, after a few minutes after that, there was another event. So in the beginning, there was a speculation what was this event, if there was some tectonic event that was triggered by the explosion, if it was some collapse and so on. Now, what you see here in this plot is the mirror symmetry of the two events. We have normalized the waveforms, and we have flipped the waveforms of the second event. And as you see, there's a perfect match, but there's a flip in the polarity. And we have fitted these events, and we have, okay, we did also some uncertainty analysis, low DC as expected for the two events. But you see, one is the explosion and the second is the collapse. And we have modeled it as an opening and a closing crack. Later, this model was also validated by other methods. Another example is from a relatively, let's say, small event, recording very large distances. This is again from Brazil. We have a 4 earthquake, but at very large distances, larger than 400 kilometers. So we can use ISOLA here, but standard, let's say, ISOLA. We have a very poor fit and wrong solution, as you can see here. This is the correct solution. We know it from other studies. But if we apply ISOLA in these stations here, we get a very wrong solution, which is, of course, due to the inaccuracy of the crustal model for such large distances. So what we can do, we use the envelopes of the waveforms. So using the envelopes, we managed to get a similar solution as the reference correct solution, basically because the envelopes are less sensitive to the inaccuracy of the velocity model. Besides the envelopes, of course, because you lose the phase, you need also some polarities. Examples of massive data application of ISOLA for tectonic interpretation, but there are many examples like this. And now I move to part 2. Well, this is for me the most interesting part of ISOLA, because here we model the rupture, we model the big event as a multiple point source. So we have many point sources, distributed either on a fault plane or on a strike line of the fault or whatever. And then we iteratively compute the moment tensor, the position, the time of these, let's say, sub-events. So once we find one sub-event, we subtract the waveforms for this specific sub-event from the data, and then we continue with the next one, the next one, and the next one. Besides this type of iterative deconvolution, ISOLA has also another joint inversion methodology included, which is the NLS, which also can derive two sub-events from the waveforms, but up to now just two of them, not more than two. So why do we have to use multiple point source? Why not using just a single point source? Because of course you probably know that we can model the earthquakes either as a single point source using very low frequency and larger distances, or using higher frequencies at smaller distances. The multiple point source is usually equivalent to major patches of slip inversions. So as I said in the beginning, this is not a slip inversion, but it can be considered as the initial step of the slip inversion, let's say. We have a multiple point source model, and this can be used as a guide when we are doing the slip inversions, because for those of you that are not familiar with the slip inversion, these are usually not stable inversions. So the MPS can be used to stabilize the solution. For historical reasons, I have included here the very first multiple point source application of ISOLA, which was actually the first application of ISOLA. It was the Lefkada earthquake in 2003, 6.2 earthquake. These are the Kefalonia and the Lefkada Islands, 100 kilometers to the west of Patras. And we have a 6.2 earthquake. You can see here the aftershock distribution, and you can see that we have a very strange aftershock distribution. This is the epicenter. We have aftershocks here and aftershocks here. And when we analyzed the waveforms using the multiple point source method, we found 4 sub-events, one major sub-event here and one major sub-event here, and plus 2 smaller sub-events in the north area here. So we proved that this was a multiple rupture. Actually, it can be considered as a double rupture. And in this area here was a huge asperity that broke in 2017. Other applications, we have done a lot of applications in Turkey. Turkey has very strong events, and you can see here that we have computed with ISOLA 3 main source episodes. This is the Elazig earthquake in Turkey, and we constrained the focal mechanism for these sub-events. You can see that the 2 major sub-events, they have similar focal mechanism, but the third one is of slightly different type. This is an example from China. And in this example here, from the waveforms, we have found 2 different types of mechanism. One strike slip at 0.8 of the grid and a thrust fault at 0.6. And they operated with a 3-second difference and 3 to 9 kilometer distance difference. This is from an article in Nature from Hicks. Stefan Hicks is using ISOLA in many applications. And you can see again here that they have used ISOLA to derive multiple point source solution for this event in the Atlantic. Routine use, it is used in many observatories as a routine tool. And Nikos will discuss later about the automation of ISOLA. And I will conclude with a summary. So as I said, it was developed, it is being developed actually, we never stopped since 2003. MATLAB and Fortran packages, single and multiple point source models. The multiple source models can reveal the presence of several faults in a big event. We are trying to update the software and correct bugs and add new tools, but okay, we are not very successful in this, I would say. All the updates are derived from the cases we are studying, from the research we are doing. As I said before, there are also different methodologies to treat smaller events, to use polarities, envelopes, and so on. And this is a useful reference if you want to start with ISOLA. It is a review of the method, the applications of ISOLA. And thank you for your attention, and sorry for taking so much time.
Okay, thank you, Prof. Sokos, for the very interesting presentation. We were very grateful to be able to listen to the ISOLA presentation directly from Prof. Sokos. Many of my friends and also I also use the ISOLA in our study and research. Okay, we will move to the Q&A session. Participant, if you have any question, you could raise hand to ask directly or type them in the Q&A session. Okay, Ade, please you could deliver your question. Please let us know where are your affiliation from. Thank you.
Okay, thank you, Miss Dian. Did you hear do you hear my voice?
Yes, clear.
Okay. Okay, let me introduce myself. So my name is Ade. I'm a postgraduate student from ITB, but currently I at a national research and innovation agency from Indonesia. Thank you for your tremendous presentation, Prof. Sokos. Actually, I use also ISOLA for my thesis and dissertation, and now I have a few questions about estimation of moment tensor using ISOLA. Maybe the first question is how to get a good parameter of frequency filter for fitting between synthetic and observed models in inversion window. Because I try many trials to get.
Can you repeat the question slowly, slower? Yeah.
Okay.
How
First, how to get a good parameter of frequency filter for fitting between synthetic and observed model in inversion window. Because I have tried many trials to get a number, a good number between a low frequency and higher frequency to get a better result in inversion. And maybe the second question, I want to ask about, I tried to estimate the moment tensor using few software like ISOLA and other software such as time domain inversion moment tensor. If you ever heard about empty time. And in my study case, I found that the inversion result from ISOLA show a differences compared to using the time domain inversion with empty time, especially for small to moderate magnitude on very small earthquake, less than 10 kilometer actually. And what's your opinion about this, Prof. Sokos? And I tried to analyze this anomaly and I have a tentative conclusion, but I don't know is it true or not. Is it because the free surface effects on the shallow depth that makes the range of the mismatch bigger between the green function model and the observed model? And what is your opinion about this?
I do not understand the explanation you said.
So I tried to analyze this anomaly and I had a tentative conclusion. Is it because of the free surface effect on a shallow depth that makes the range of mismatch bigger between the green function and the observed model?
But you said that you have a discrepancy between the two different softwares for the same event.
Yeah,
Okay.
I use the
So
same.
it means that the two, I'm not familiar so much with the other software. So it means that the two softwares should treat the green functions in a different way, right?
Yeah, it's right.
Is this true? Okay, for ISOLA, you know that we are using discrete wave number. I don't
Yeah,
know what
I know.
is the other software using.
To generate the
To
green function
generate
model.
the green functions, yes.
Yeah. It's
In
very different.
general, we do not have many comments about difference between ISOLA and other softwares. But I
Yeah,
cannot exclude this, that there could be some small, but I would say small difference, not big difference.
yeah.
Now the first question is really the core of the inversion. Okay, how to define the frequency range? This is really let's say tricky, and
Yeah.
someone needs to understand the problem very well. So
Yeah.
you have to define two boundaries. One boundary is the low boundary, and the other is the high boundary. So these are affected by different things. The high boundary is affected by the resolution or the quality or the accuracy of your crustal model. We have, sorry again, but so we have some in the publication I showed before here. If you find this publication here, we are actually trying to give guidance on how to solve this. So in principle, there is an empirical rule that you cannot use distances larger than 10 minimum shear wave wavelengths. So based on the wavelength you are trying to use in the inversion, you can define the maximum distance, and this will define you also the higher frequency. Now, the lower frequency, it depends on the noise you have in your stations. So this is why we have all the tools for analyzing the noise filters, and we filter the waveforms with different frequency bands and so on. So this will define you the lower limit, the noise you have in your data. But you will do this either per case. So you have one earthquake, you take all the waveforms, you study, you do the filtering, and you see where the noise starts to grow higher than the signal in the low noise, the low frequency area. So if you find this, then you start the inversion above this. Of course, you must have a window between the low and the frequency that your signal is strong enough, and it is free of some disturbance and so on. If you cannot see, then you cannot, if you don't have this window, you cannot use the waveform. And this frequency, let's say window or frequency band better, should be long enough. You cannot use, let's say, 0.02 to 0.03. This is very small frequency band, and you get some strange sinusoids and so on. You must have a large enough frequency band to use in your inversion. But the things you have to keep in mind is noise in the lower part of the spectrum, and accuracy of the crustal model in the high frequencies part of the spectrum. So as I showed before in the example, if you are very close to the source, if your distances from your stations are very close to the source, then the accuracy of the crustal model is not so critical. And you can go to higher frequencies where your signal is strong and so on and so on. The problem that arises there is that when you move at very short distances, you have to be careful not to move to distances comparable to the fault length, because your earthquake then is not a point source for your network. It is an extended source, and ISOLA is considering point source, so you cannot approach, let's say, too much the epicentral area. So it depends of your application, but you have to consider all the things I tried now in a few minutes to explain. I probably failed to explain clearly, but you know, we can discuss also again, or go through this publication here, and if you have more questions, we can discuss.
Okay, thank you very much, Prof. Sokos, for your answers.
Okay, thank you. We still have some more questions, Prof. Sokos. There are two questions from Andri Kurniawan. Dear Prof. Efthimios, my name is Andri Kurniawan. I want to ask for micro-earthquake data. Can be used full empty inversion type? And what is the difference with deviatoric empty type? Thank you. Would you answer?
Sorry, the difference between
What
is
is
it
the
in chat? I can see the chat.
yes, it is in the chat box, Prof.
Okay. Yeah, if you have a what does it mean, micro earthquake data? Okay, if you have micro earthquake data, yes, you can use full empty inversion. We are using the full empty inversion type of inversion when we, let's say, suspect or we expect that we have some isotropic component of the source. So we are in an area of, let's say, volcanic area where we can expect some isotropic part of the source, or we have an explosion, as I showed before in the example. The deviatoric type, it is just again a seismic source that has zero isotropic part. Okay, so it is DC plus some CLVD. I'm not sure if I explained. And also, in principle, you can go on and use full empty inversion type. There is no restriction on that. And based on the results, you know, if you see that the isotropic part is close to zero, then you can consider that, okay, I can now move to the deviatoric type. I proved that it does not have an isotropic part, and I can now continue my analysis with deviatoric type. I have to say here that you need very good data when you are trying this type of inversions. Good distribution of the stations, good location of your event, good signal to noise ratios, etc., good model, and so on and so on, if you want to go to the full MT analysis. And also, ISOLA can also do some uncertainty analysis of the isotropic part.
Okay,
And
thank you.
I see the other one. Yeah, okay, sorry.
Yes.
Yeah. I see the other question is based on your experience, what is the minimum station number at distance used to retrieve a relatively good empty solution? Is it 3 stations enough or not? Yes. This is again a very good. I think we are treating this question also in the publication. This is a question that comes often. In principle, you can use a single station. Okay, but I don't think yet you'll be able to publish this result with one station. 3 stations. Okay, you have 3 stations. What is the distribution of the stations with respect to your epicenter? Do you have 3 stations around your epicenter? Then probably you get a good solution. Probably. You must do all this uncertainty analysis. You have to do the jackknifing part and so on. You can compare your solution with the polarities. You know, it's a very difficult question to answer if we don't have a specific application. If we had a specific applications, we could go through the data, we could go through all the other metrics and say that, yes, this solution is acceptable, although we use only 3 stations. But if you want to be safe, you should use more than 5 or 6 stations, and then everybody will be happy, I think. Because the reviewers will not like the 3-station inversion, I'm sure.
Okay, thank you, Prof. Sokos, for the answers. I also have some question. May I ask? In my experience and also my friends' experience in using ISOLA, if we set the frequency 1 and frequency 2 frequency band small, the variance reduction is improving, but the frequency content of the waveform is so monochrome, like a single frequency. But if we enlarge the frequency band, we will have some more frequency content of the earthquake, but the variance reduction is getting lower. And what should we do, Prof?
You should use a larger frequency band. You should not restrict your frequency band very much, okay? Because as I said, you just get some sinusoids, and then the algorithm, it will fit them, for sure. It will move a bit the source, and then it will fit these sinusoids. And then you get a very good variance reduction. But this is not true. You know, this is an artifact. You should use larger frequency ranges, although your variance reduction will, you will have a lower variance reduction, okay? Now, what is the acceptable variance reduction? Again, very difficult to answer. In principle, we say that if we have variance reduction larger than 0.5, we consider this solution acceptable. But you must always look at the correlation plot to see the stability of the solution, define if you have a very stable solution, a very small FM var, then you are more happy with your solutions, although your variance reduction is not so perfect, let's say. I would not suggest using, you know, many people are using very small frequency bands, and of course they get better variance reduction, but this is not true. Another problem that comes if you are using smaller frequency bands, let's say restricted frequency bands, then you get in the correlation plot, maybe you have observed this, you get stripes of large correlation. You don't get one area of large correlation. You usually get one area with large correlation before the origin time, and one area of good correlation, similar number of correlation after the origin time. And in these stripes of similar correlation, the focal mechanisms are with exactly the opposite. This is an artifact of very small frequency band used in the inversion. If you extend your frequency band, then you will remove this. But as I said, it depends on your data. If you have noisy data in the low part and you have inaccurate models, so you cannot move too much in high frequencies, then your frequency band is limited. So you either find a better model or you get better data.
Okay.
Or you're trying to use the other methods. You can use envelopes. Okay, you can use some other method, not waveform inversion.
Is it okay if we set the different frequency range to other station in many station we use in frequency band? Because we have that option, right?
Yes, you have the option to set a different frequency range per station. We're usually applying this when we mix broadband stroke motion networks. The strong motion instruments, they usually have lots of low frequency noise. And okay, because they're not so sensitive in this area, it's okay. So we use higher, let's say, F1, Okay, we don't go in the strong motion stations too much to the low frequency part. We go a bit more to the high frequency part. And in the broad band stations, we go more to the low frequency band because they are better in the low frequencies.
Thank you, Prof. Sokos.
In principle, you can use it in any station distribution. You can use different frequency bands.
May I also ask about the frequency band? What is the minimum frequency band that we could still use and avoid the artifact? Could you suggest?
In principle, you can use 0, but you will have a lot of noise in this. So, for example, for very large events, here in Greece, we go to 120 seconds because you know you have broadband sensors that are 120 seconds. But this has to be a very strong event that has a lot of energy in this frequency band. Okay, this is something else you must consider also. If you are studying a small event, this event will not have energy at low part. So there is no need to move to lower part. You'll just have noise there. If you have a strong event, then this strong event has a lot of energy in the low frequency part. So you move to the low frequency part. You don't need to go to the higher frequencies because your model will start to give you errors there. So it's a different view when you study small and larger events. Now, and this is why we have automatic softwares working on these methods. Based on our experience, Nikos will explain later, based on our experience of analyzing manually hundreds of earthquakes, we roughly know for our network what is the frequency band suitable per magnitude and per distance. So it is a knowledge that comes from the everyday application of this method.
Okay, thank you, Prof. Sokos. Well, we should learn from each of the earthquake for the frequency band. Okay, right. Yes.
This is why we built in ISOLA the tools to do this filtering. In principle, you should go through all your stations, load your waveforms, and start applying filtering in different bands. And start with the higher frequency bands and move slowly to the lower frequency part and see where the noise appears and destroys your signal. And then you know that I cannot go lower than this limit. Okay.
Okay. Thank you, Prof. Sokos, for the really insightful answers. Participant, do we still have any questions from the participants? Okay. Maybe if we don't have any more questions, we will save time and we will move to the next agenda. After we will have a break about 10 minutes. After the break, we will move on to the Gisola session. Okay. We will have a break in 10 minutes. Hanifa or Ila, would you help me for the break slide?